Yes. So as usual, we start with some review on the homework last time. Let me see, where's my laser point? Okay. So last time we focused on the functional equations, right? And these kind of questions are always challenging, to be honest, especially when you have a question with combination of multiple variables, and also with the different known functions in the function description. That will be even challenging. The first one, I don't think it's so challenging because the first one you can try to plug in, for example, the x with x minus 1 divided by x, and then you find again in the second equation, the second term has the 1 over 1 minus x, and when you plug this one in, then the second term becomes x. So actually, this is a system equations of three variables or three equations. So it's easy to solve it, and then you get fx, and let's say the equation for xf. The only attention point that you have to define the domain, yeah, because many of you or all of you can easily find this one, but it's better to always define the domain. In this case, x cannot be 0 or 1. So that's this a part of a division of functions, right? So because it's asked to find the function, bear in mind that in the definition of functions, it's not only the, let's say, equation or formula, but also the domain. Now you have the domain as the real numbers, or as integers, or as complex numbers, for example, and in which, let's say, domain is not defined. In this case, x is not defined as 0 or 1. Yeah. Okay. Second one is something about, let's say, trigonometry functions here. It's cosine. In this case, we have two variables. So I saw some some solutions where you plug in the both x and y with some special values like 0 or pi or half pi. But then you got some special values of this function. It won't help a lot for you to find in the formula of this function. So the idea is that you always keep a variables in, not, for example, in this case, x is 0, y is t. Not for both as 0. You can also do x is 0, y is 0, but then you won't have an equation where the variables are still in. So you see, in my solutions, I always keep t in one of the x or y, so that you still have a expression of ft or f minus t in your equations. So by these three plugins, we create three different, let's say, forms of the function. On the right, make use of the cosine sign, because here you know the cosine, the sine, especially using the f half pi is 0. We use the half pi of 0, or half pi is 1, sorry. Yeah, half pi is 2, okay. F half pi is 2. So actually, this one is known. This one is also known because independent on t, cosine half pi is 0. So then actually on the right, you have all the constant or known values. On the left, you also have the system equations of three variables. Yeah. Then the third one is also straightforward. I think everyone found already the recursion function, the fn and fm-1, fm-2, because you see if I move the n times fm-1 here, then we have a good recursive function. So by this, you say fn minus 1 is minus 1 over n times fn minus 1 minus fn minus 2. So you see here, actually, you can define it as a q or gx or gn, whatever, and you can also directly extend it back to f3 minus f2. So that's on the left. You have also kind of equations, but it's not a telescoping, but telescoping by multiply. So you can multiply all the equations because on the right you have the same terms except for the first term. On the left you have only this term left. So then easily you get a, let's say not a sigma, but it's pi, meaning that it's also kind of factorial of n divided by 2. Yeah, so that's something you can formula with that because you know the f2 and f1. And for the rest, again, you do a telescoping now because then it's the difference between these two terms. You know it's already something about factorial of n, and then you just sum them up. So that's why you get the sigma. Get a sigma, and of course, at the end we find this is a alternating term is minus 1, 1, minus 1, 1. Yeah, so you cannot simply simplify it further. So you keep it as such. Okay. Number 4 from Vivio. It's a pity that nobody got a full mark here. Because you show already a lot of submissions showed already an answer. The answer is correct, but of course we have to show this is the only answer. The only answer means that it's necessity. But you have to show it's necessity. From here, it's easy to construct a q, a function of q, where it's shown as this one. Yeah, the p is q is p divided by k plus 1 minus k plus 1, and then we got the q. All the q terms are the same. All the q terms mean the k from 1 to 12. So we get q1, q2 to q 23 is the same because it's q plus 1, k plus 1 minus qk is 0 when k is 1 from 22. So actually there are 23 points where the q has the same value. So if you define the r, where is q minus q1, then immediately the r1 is 0, and for all the k1 to 22, because r23 is also 0. So meaning that rk has 23 roots. Yeah, rk is equal to 0, has 23 roots. But since p, q, r, all of these functions has up to 23, the order is up to 22, sorry. The degree is at most 22. So meaning that's polynomial up to 22, but you have 23 0 points. What does it mean? It means that the RK is 0. RK is 0. So it's always 0. Yeah, it's always 0. And then we can just say, okay, the Q is Q1. So QK is always Q1. And then back to the PK, we got PK, this formula is P1. So then it's always something about P1, but you can argue what is P1 is, but P1 is P1. P1 can be any other numbers. It's defined by, because it's not defined in the function, so not defined by P1, so you can use P1 as a constant. So it's always very interesting. If you have F1, F0, it can always regard as a constant. Yeah. So that's something also important in the last two questions. I'm not going to deeply into how to plug in these numbers, but for example, in the question number 5, you have also here, you find the fx fx is 2x plus 2 times f minus 1. You might think, what is f minus 1? I could find it. It's like something about f0 or f minus 1. I don't know, but it's a constant number. You can always regard it as a constant number. And then at the end of the day, you say, okay, I've plugged in another value. I try to find what the constant number is. That's possible. Yeah, that's also possible. So you first get a linear equation with, let's say, a slope of 2, but I don't know what the intersection is. I only know c is 2 times f minus 1, but you can plug in again to the original equation and find c is actually equal to 4. And then you get the full, let's say, expression of its function. Yeah. You can also do some verification to see if c is indeed 2 times f1. You can plug in the x is minus 1, so you get 2. Yeah, indeed, that's 2. C is 4. C is 2 times f minus 1. The same as the last one. I got those chat here. P1 had to be minus 2. Okay, I will see. I will go back. So the last one is also same. The last one, you get also the constant f(x) of f1 times x. So some of you stop here, but of course you see immediately when x is 1, so actually f1 is the c. f1 is the constant. So you can also plug in x is 1, then you get fx cx. Yeah. So that c is indeed the same c as here. So let's back to number 4. So P1, what vector says, P1 must be minus 2. P1 must be minus 2. Then I will go back here. So if I go back to this equation, so let's see if the P1 is, for example, 0. Would it be possible or not? Yeah, I would say if P1 U1 is 0, what happened here? And the K is K, this K is 1, so that's P2 minus 0 is 1. So the P2 is 1. Yeah, and then we got P2. No, P2 is 3. P2 is 3. Yeah, P2 is 3. P1 is 0. And the K minus 2, K is 2. So the 2P3 minus 3P2, sorry, 3P2 is what? 4 2 is 7, yeah? So the P3 is, this gives you 9, and then minus gives you 9, and then the 16 that gives the 8, and so on. So you can still do that again. So you can build up the full series of P. P1 is 0, P2 is 4, is 3, and P3 is 8, and so on. So it's not necessary P1 is minus 2. You can full follow these recursive functions and build up the full sequence. So all depends on the P1, but P1 is not so important. Yeah. Okay. So you can vector you can expand this further. You can also let P1 is 1 to try if it's also fulfill all the conditions of this in the question. Okay. So now let's switch to the new content. For today, what we are talking, a very interesting one in the combinatorics. Something we never taught before, but we know some challenges before. But in this lecture, we're talking about some general techniques we call invariants. Okay, so we start with one example. I hope you did already some pre-reads. So basically, it's very typical combinatory questions. Something about plus sign, minus sign, something about parity, odd, even numbers. So it says in a square of 4 by 4. So actually you get 16 cells or squares, and each square is assigned with a sign of plus or minus. So here we get 1 minus, but a 15 plus. And the rule is that in each round you can select one row or one column, just change all the signs to another sign. Change the plus to minus or change minus to plus. And it's asking, is it possible that after a certain number of runs, all the signs can be converted to the same, to a plus? All the signs change to plus. In this kind of question, it's always, most likely you can say it's impossible. The answer is impossible, but you have to prove it's not possible. So I think many of you are able to solve this kind of question. You have, plus, I mean, you change this plus to minus and minus to plus. So it's kind of a parity, the odd number to even number or even number to odd number. Yeah, it's always linked to the parity. So now we'll think about, how to prove it. Yeah, how to prove it's possible. So you focus on the rules. You focus on rules, you can choose one row or one column to change all the signs. So actually, in each round, you change the sign of 4 squares. Yeah, you change the sign of 4 squares. No matter it's minus or plus, you always change the sign for 4 squares. And what we can show, because in the first or the initial stages, you have 15 plus 1 minus. So basically, if you multiply all the signs together, and all the 16 signs together, you will get a minus. Because 15 plus 1 minus, you multiply all the signs together, you get a minus, right? And at the end, the target, we aim to have a 4 by 4 table consists all the plus signs. So if all the 16 squares get the plus signs, if we multiply all the signs to get the plus. So that is the change. You've got the minus to plus. But if you select, in each round, you select one row or one column, you change the sign of 4 cells. So it's always changed by an even number. So in the multiplication, it won't change, meaning that I don't care how many minus there or how many plus there. I change sign 4 times, but the 4 times in the multiplication is no change. It's no change. So this is a contradiction. This is a contradiction, meaning that, okay, it's not possible because in each round of the possible operations, you will be not able to change the sign of the product. The product remains a minus, but you are aiming to have a situation where all the signs are plus. So that means the product will be a plus. So that's also possible, yeah? So that's very easy example to start with. Now we have an exercise. So instead of 4 by 4 table, if in this case we have 5 by 5 table, and it's also still 1 minus sign, but all the 24 cells are placed with plus sign. The same rule, if you select one column, one row, you can change all the signs here. And how to prove it is possible or not possible? Yeah. Who have tried this before? Okay, so you can just type in the chat if you get yes or no. Yes means that you find the proof. No is that I didn't find the. Okay. Okay, 小石头 yes, and Ding Ding no, no, Ding Ding is not. And other student, Victor yes, okay, good. And Andrew, Yuchen, Lucia. Lucy and Yuchen. Lucia, yes. Okay, Yuchen, yeah, no, okay. So in this case, we cannot simply use the strategy we use in the example, right? Because in this case, in every round, we change the sign in the row of or a column. It will be changed by 5 times. 5 times meaning that we indeed change already the sign of the product. If we just multiply all the 25. So every time we change the sign, so it's no longer a constant. It's no longer, we will call it later invariance. So we need another way. We need another way to change to prove it. So here, what we are going to do is we focus on a 2 by 2 table. So because we have a minus, so it's easy to find a 2 by 2 table, either here, it's also, or here, it's the same. So you can freely choose one 2 by 2 which contains the minus sign. It's always feasible, right? And now think about the operations of each round. So there are 2 cases actually. If, for example, I'm going to use my pen. If we choose a row or column which has no impact on the 2 by 2, of course, the product of these 4 signs won't be impacted. Because of something else, some squares else are selected. So there's no impact on the product of 4 signs. But if indeed a row or column just passing through this 2 by 2 table, and then it's changed, of course, by 2. Yeah, changed by 2. Or this way, you change it by 2. That means if we focus on the 2 by 2 table, we can use the same rationale or the same reasoning from the example, because the example is a 4 by 4, right? And now we focus on 2 by 2, meaning that for any operations on this 2 by 2, the product of the 4 signs will be changed by 2. Will change by 2, either in a row or in a column. It's changed by 2. So meaning that the product of the 4 signs will still a constant, will be a minus, So that means it's not possible. Yeah. By the end of the day, we're aiming to have all the cells turned out to be plus. It's not possible. So we use the same, but you see, the clever thing is that we do not care the other cells. I can easily focus on a 2 by 2 table, and we can use the rationale from the example. Yeah, from the example is 4 by 4, but 2 by 2 is also even number by even number, so we can use the same. Yeah. So that is called invariance. The invariance in the combinatoric problem is some value, quantity, amount, which is not changed, from one round to another round according to the rule. Yeah, we can call it operation or transformation. Sometimes you have the transform, sometimes you do the addition, you do a multiplication, you switch a card, remove one number, whatever called operation or transformation. But according to the rule of operation transformation, this amount, this quantity will never change. So we call it invariance. So invariance is a constant number, a constant value across this whole procedure. And of course, the key to this question is that to find in the initial status, the variance had such kind of value, and in the desired ending situation, in the desired ending, let's say, iterations, you have another value. Yeah, if you have another value, and then it's not possible, right? So in the example, we use a product of 16 signs. In the exercise, we actually is a product of 4 signs. Yeah, they are invariant. They never change. But the aim is to turn all the minus change, the 1 minus change to all the plus signs. It's indeed is changing. The aim is to change it, but that means it's not possible. Yeah, so you got the idea of what is the invariant. Yeah, okay. Now, sample 2. Yeah, so let's say it's not always using the numbers. Sometimes you have also kind of geometric shapes, like a cube, So in this game, you say, yeah, we have 8 vertices in the cube, and each vertex has a 1 number, like 0 or 1, but actually we get only 1, but all the 7 other vertices as 0. And the rule, what is the rule? The rule is in each step, we select one edge, for example, this edge, and then add 1 to the both end of this edge. For example, if we select this edge, and then it's increased to 2, and this is 1. The next step, we select this edge, and this can 1 and 1. So you can freely select one edge and add ones on both ends. So it's asking, is it possible in several such steps, all the 8 numbers become equal? So then for this kind of question, we say, what is the invariance? What is invariance? Because it seems all the numbers are increasing, right? All the numbers are increasing. But what is the invariance? We have to say, okay, something above the number. Not only the number itself, but above it, And we see in this case, actually, when we add the numbers on the edge, so the total number will be increased by 2. So because here is increased by 1 by 1. So if we focus on the sum of the 8 vertices, it will be increased by 2. So naturally, we can find, okay, increased by 2, something is not changing, but the amount is increased by 2. What is invariance? The parity, of course. The parity of the sum, right? The parity of the sum does not change because every time you add 2 to the sum, yeah. So the initial stage, of course, is easy. We get only 1 and others are 0. So the parity of the sum is 1, which is an odd number. And the end situation we are looking for is all the 8 numbers become equal. I don't care it's odd or even number, but you have 8 equal numbers. So this number times 8 will be even number. The parity will be even. So initial state is odd, target stage is even, but in each runs, the parity does not change. So that is a contradiction. Yeah, got it? Easy, right? Now, exercise 2. So it's just one change. The rules are the same, but only one change is initial stage. We have 2 ones instead of only 1. 1 ones, yeah? I have 2 ones here. So the initial stage is already like a sum of these 8 numbers is 2, is already even. And then we cannot use the same rationale as the first page, right? Because the even, how can we defend us? Who tried this out? Who get it? You can say yes or no. You found it? Okay, good. Good. And who else found it? Victor, no. Yuchen, yes. I did it. It is possible. Yeah, Andrew, you know how to prove it? Okay, the variance quite complicated. It's by Xiaoshito. Not really. Okay, you know it's impossible, but you don't know how to show it's possible. Lucy, have you tried it? No? Okay, okay. So as I said, now we cannot focus on the parity of the sum, yeah, because it's already an even number. So that's involved another trick, another skill in this kind of invariables. So instead of think about all the 8 vertices, we have to think about, we might able to classify these 8 into 2 groups of vertices. So what are the two groups? Think about a regular tetrahedron. Now you know a cube has 8 vertices, but 4 of them form the regular tetrahedron, and the other 4 also form the tetrahedron, right? Tetrahedron. And then you see again, what is the size? Now I'm going to write the size here. For example, this is age, this is age. So the age will anyway connect 2 vertices. One belongs to one tetrahedron and another belongs to another tetrahedron. So meaning that if we add one number on the both end of an age, the sum of the 4 points or 4 vertices in each tetrahedron will be increased by 1. Yeah, so that means the difference of the sum of the 4 vertices of each tetrahedron will be an invariance, will not change. Yeah, because I don't care which age you are choosing, but you add 1 to this tetrahedron, you add another 1 to another tetrahedron. Yeah, the difference will be a constant. Now think about the initial stage. The initial stage, very interestingly, the 2 ones belongs to the same tetrahedron. So meaning that the sum is 2. And the sum of another tetrahedron is 0. So difference is always 2. Difference is always 2, no matter how many rounds you're using, no matter how you select these ages. The difference is 2, which is invariant. But what we are looking for, the target is all the 8 vertices are equal. So meaning the difference of this sum of the 2 tetrahedron will be 0. So that is contradiction. Yeah, that is contradiction. So I do like the combinatory questions because it's always challenging you to think in another way around. Yeah. So you do not need a very, let's say, sophisticated theorem. You don't need a very extensive or intensive knowledge about mathematics. It's just coming from the basic rules, coming from the basic logic. Yeah. Okay. So you might think, oh, it's always impossible, right? So as Andrew said, okay, I do see it's impossible, but I don't know how to prove it. So the invariant, of course, is used often to solve this kind of question to say if it's possible or not possible. And if we find the right invariance, we can use it to show, okay, it's indeed not possible. But do we have other applications? Do we have any other applications use invariance? Yeah. So now I'm showing some good applications because in sometimes you have to find the answer, but of course, due to the different selections, because I say Alice is free to select 2 numbers from the blackboard, or Bob is free to discard 2 balls from the box, but the combination number is so huge, you cannot solve it by brute force, saying, okay, I first try these 2 numbers, then try another numbers. There'll be a huge number of trials, right? So now we use the invariant here. So on the blackboard, The Bob writes 24 signs in which 10 are plus and 10 are minuses. So 10 pluses, 15 minuses. So altogether 25. And the rule of the game is that Alice can select 2 and erase 2 signs. Okay, select 2 and erase 2 signs. And if the 2 signs are the same, then she write a plus again on the blackboard. So erase 2 signs and add 1 plus. But if they are different, and then she add 1 minus. So basically, after 1 round, the number of signs decreases by 1 because it's 2 are erased, 1 is added. So actually, the total number of signs decreases by 1. Yeah. So at the end of the day, of course, it will result in only 1 sign on the blackboard. Yeah. Maybe after 24 rounds, there's only 1 sign on the board. So it's asking which sign is remained last on the board. And this apparently is independent to how Alice selected signs in any order. Yeah. So that's a kind of question. It's not always asking is it possible or not possible. Now it's asking what is the result. Yeah, the plus sign or minus sign as the last one. Yeah. So in this case, we also want to find the invariant. So if the invariant can tell me, okay, which quantity, which value is not changing, and of course at the end there's only 1 sign on the board, I can also apply this invariant, helping me to find what the sign it is, right? It's a plus or a minus. So again, here you see the plus and minus. It's very natural to think, oh, that must be parity. Of course, parity is always plus signs. And according to the rule, the 2 plus signs will give you 1 plus. The different signs will give you a minus. So it's natural to think, oh, the 2 difference, I can keep the minus as odd, for example. The minus is odd. The plus is even, for example. So that means if we remove 2 even, and we will add 1 even, or 2 odd, we'll add 1 even. And if we erase 1 odd, 1 even, then we'll add 1 odd. And see, by this, it seems that the parity does not change. So actually, the parity of the sum of all the signs will be the invariant. And then the inertial status is that we get 10 pluses and 15 minus. So odd number of odds. So the sum will be odd. And the sum will be odd. And at the end of the day, when we have only 1 sign, because the odd is the result of the invariant. So meaning that if we have only 1 sign left, it must be odd. It must be odd. And what is odd? Odd is minus. Yeah, we can translate it back to the sign, the odd is minus. So that is one application to use the invariance. Yeah, very useful. Well, this exercise, oh yeah, oh, it's already turned out. Okay, exercise, I forget to make it, let's say, animation, okay? So let's do it together. Who tried it? Who tried it? Because in your pre-read, maybe you don't have the answer here, but then I show already the answer here. Who tried it? Exercise 3. Hey, okay, you don't understand the question, okay. So Ding tried it, but I don't know if you have the answer. And Yucheng, Victor, Lucy, Andrew also tried it. Okay, you don't know how to prove, yeah. So the displays, yeah, what is display? Displays is to moving, is to changing, for example, changing positions. So actually you have a triangle, and each time it can flip over one of the sides. For example, if A, B, C, And each time you can do, okay, I do the flipping over the AB. So then you have the C prime here. So this is flipping over the side of AB. But you can also do a flipping over the side of BC. So you get A prime here. Or you can flip over the side AC. So you get a B prime here. So you get, again, for example, you flip here. And the next time you can again flip maybe over here. So you get A here. And the next time you flip over these sides, you get there, and again and again. Yeah. So it's asking after flipping over 25 times. And this triangle just go back to the original page. So it's overlap each other or superimposes itself perfectly. Yeah. Perfectly. So that's asking the triangle itself is proof that triangle is isosceles. It cannot be a triangle of other, a random shape, but it must be isosceles. Okay, so let's try it out because of the flipping. So I think we learned that in the symmetry, or maybe no, symmetric lessons only for for 1 grade younger. So flipping, so meaning that I can write ABC, okay, ABC like this. If we do a flipping, it's always like over the sides. So you get, for example, C is here. So if we do the flipping, something is changed, something is not changed. So what has changed? What has changed? So say when the ABC is flipping to the ABC prime, you see the order of the letters A, B, C. Here you have clockwise, but in the A, B, C prime is anti-clockwise. Yeah, the order of these 3 letters. And it's independent on which side you're going to flip. You can also flip A here. So you get A prime here. So you can try ABC. ABC is now counterclockwise. And you can also flip B here. Yeah, for example, B like here. So ABC is again counterclockwise. So every time you change the order, of these letters. And then, of course, 25 times, meaning that you start with ABC. You start with ABC like clockwise, ABC. And after 25 times of flipping, you will always have anti-clockwise. But it's said it's arrived at the original place. So I mean that if you have A overlapping with A, and then you should have B, C, something like that. Yeah, instead of CB. So if the triangle is not isosceles, then you have these distinct interior angles. It's not possible. Yeah, because imagine here you have another angle like CB. You have another angle, so you cannot superimpose itself with yourself. Superimpose it with yourself. So that means it's always necessary to have the same, at least one pair of the interior angles is the same. Yeah. So that means the triangle should be isosceles. And it is also possible, yeah, it's possible if you say, okay, I have a BC like this, a very narrow, very small vertex angle, like 360 divided by 2025. And this A, and this is B and C, and you just flip over the AB and flip the AC, flip the AB again, and dot, 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 dot. And after 25 times of flipping, you are coming back at ABC, but of course it's ACB, you have ACB. But since AB and AC are equal lengths, you have the isosceles, so ABC will be superimposed by the ACB perfectly. So that is the feasibility or necessity. Okay. So now the question is that, of course, how to find the invariant is so useful. Yeah, it's so useful. But of course, the challenge here is that how can I know it? So you can try it first. For example, some common quantities like sum or product, especially talking about the parity, plus, minus. You got the product. Something we can say the sum should be the invariant. And for the geometric shapes, you have the area, parameters are not changing, for example, and so on. But more advanced, you can also focus on some modular operations. For example, the remainder are not changing. Yeah, we use also for some games as well, and also some coefficients for the polynomial nationality. For example, if you plus, minus, or multiply a fraction, you always give a fraction because the rationality keeps. It's also a rational number. It cannot be go to an irrational number, for example. And as I showed already, sometimes you have to divide the vertices in two groups, and you see the difference of the two groups, or is any other unchanged values between these two groups. Yeah, can help. But of course, it's not the general rule. It's not the general rule to show, okay, how to find this invariant. Okay, one example. So the farmer Bob, has a square of 1 kilometer times 1 kilometer. And of course, it's already fenced, meaning that the outer boundary has already fenced. And he wants to divide the field into a rectangle section, 5 meters times 20 meter, or 6 meters times 12 meter. And of course, he needs some additional fences inside. And it's asking what is the total length of the additional fences. So this kind of question seems not a typical combinatorics problem, because it's not proof it's possible and impossible, or erase some numbers. It seems very strange, but I would say this is a trick here to consider the section of these rectangles, the two rectangles. One is that 5 meter times 20 meter. So if we compare the perimeter and the area, so perimeter will be 50 meter and area will be 100 meter square. Yeah. And 6 and 12, the perimeter will be 36 meter and the area will be 72 meter square. So you know the ratio here. If you notice the ratio of the area over the perimeters, always 2. 100 by 50 gives you 2. 72 by 36 gives you 2. So meaning that no matter which section I choose or Bob chooses, the area will be always double of the parameters in numbers, right? So then, of course, area is easy to have because it's 1 kilometer times 1 kilometer. The area is a fixed number, yeah. And of course, the ratio is invariant. No matter how many this type or how many this type are chosen, the ratio between the area and the perimeter is always 2. And then, of course, 1 kilo times 1 kilo gives 1 million meter square. Divided by 2, we get 500 km as what? As a total parameter. But do not forget to think about the boundary. The boundary has already fenced. So we have to reduce the length of the boundary. Yeah, of course, boundary is easier with the 4 kilometers. The 4 kilometers is boundary, and then of course 500 kilometer minus 4, but divided by 2. Why divided by 2? Because in the interval sections, one side is counted twice. There's one side counted twice by the 2 sections, right? So that's why you have to divide by 2. So at the end, you get 248 kilometers of the length is needed. Okay. Now we get to the semi-invariant. What is semi-invariance is that sometimes we do not have a variance, Or we have a variance, but we have another type of quantity which shows a trending at decreasing or increasing, or kind of model variance. So it's always changing in one way. It's not a zigzag way, but it's always a decrease, or increase. We can also use these kinds of quantity or these kinds of amount. For example, when you play a tic-tac-toe, or when you play 5 in a row, the number of cells occupied is always increased. Yeah, because it's not like, unlike a Go. In Go you can remove some pieces, but in the tic-tac-toe, in the 5 in a row, it's always increasing. And also GCD as a Euclidean, because you always decrease in these numbers. Yeah, the sum of the two numbers in the Euclidean algorithm is always decreases. Yeah, so that's also semi-invariant. We call it mono-invariant. One example is that, okay, integers are placed in the cell of 2025 times 2025. It's a really large table. And in each round, one can change the signs of the number in a row or in a column. If what? If the sum of them is negative. So if you get a sum of the rows which is negative, you can change the signs of each numbers in a row, in this row, to the opposite sign. And we have to prove that what? After find the number of rounds, the game stopped, meaning that you cannot find any row, any column is still negative. So all the sum, all the rows, all the columns turned to the non-negative numbers. Okay, to prove it, is say, okay, it's ending game, meaning that something is decreasing, or increasing to a limit, So in this case, we have actually found two amount. One is invariant, one is the model variable. Now, what is invariant? Here we consider the sum of the absolute value. Yeah, because changing the signs will not change the value itself. So out of these numbers, the square of 2025 numbers, we just sum them up with the absolute values. So y, we call it y, and the absolute values, of course, is not changing. Yeah, if you change the signs, the absolute value will not change because y is invariant. And about the x is the sum of the numbers. So saying, according to the rule, if we find a negative row, you change this row to the minus x. So s actually is the original sum, which is a negative ones, and you change the sign by changing minus s to s. The difference is 2s, which is a positive number, right? 2s is bigger than 2, actually. So actually, you increase s, yeah, by at least by 1. And we have a definition that is the sum of s is always no larger than the sum of absolute numbers. The sum of numbers is there's no way to bigger than the sum of the absolute values. So we have a limitation to y is invariant. So that's the boundary. So x is getting larger and larger and larger, but they're not exceeding y, meaning that after a finite number of games, this game will stop. So meaning that there's no other row or other columns whose sum is still negative. Because this is very important to show s is bigger than 1. Because be careful, not all things like you have a convergent number, because here you have a certain step bigger than 1. But if you say, oh, I can do any real numbers, you say, okay, 1 plus half plus 4 plus 8. Of course, this one will be 1. So it won't go to the y, right? So if you have even less, it can go infinite number of rounds, but it never exceeds your y. because now in this case, as each step, you get a bigger than 1. So that's no doubt after a finite number of rounds, you will have it reaching to the limit. Okay. And this is also one exercise. I also showed this one already. And who get it? Who tried it to get this from BMO, British Mathematical Olympiad, round 1. Okay, Shasuda got it. Who else? No? Okay. Okay. This one is also something about absolute values. Yeah. Very interesting ones because it said that for a sequence, there is also a recursive functions, but it's either or. It's not determined. It's not determined. But you see AI is 2 times AI minus 1 minus AI minus 2. So you see immediately is something about the arithmetic sequence, right? So actually you can just remove AI. So you can use AI minus AI minus 1. So if we move the AI, so AI minus AI minus 1. And it's either will be AI minus 1 minus AI minus 2, or it will be AI 2 times AI minus 2 minus 2 times AI minus 1. So actually you can find this already. Something here. But before that, we see AI are integers. So the absolute difference between this pair, each pair of these two terms will be bigger than 1. Yeah, because they are not equal, cannot be equal. And that's the first step. You say cannot be equal. Otherwise, all the sequence will be equal according to this recursive function. Yeah, so it cannot be equal. Yeah, and then of course, if they are not equal, the absolute difference will be at least 1. This is the invariant. Okay, and what is the molar variant? Is according to this recursive, we get this one, and we just make a absolute bracket. So this one must be bigger than this one. Yeah, must be no. In this case, it's equal. In this case, it's bigger. Yeah. In the second case, because it's 2 times, so in the second case, it's bigger. So you see, AI minus 1 absolute is increasing. Yeah, from I minus 1 to I. But we get a ceiling. This is the starting point, and we get the ceiling. What? The ceiling is the last one, the last pair, the A2022 and A2024 are consecutive integers, meaning that their difference is 1. So that is a ceiling. That is ceiling. And each one is smaller than before, but actually it's also bigger than 1. This is the invariance. So we have the two boundaries, both are 1. Both boundaries are 1. And that means all these intermediates values must equal to 1. And also including the first one, A1 and A0 must be 1. That means they are consecutive integers. Yeah. So, okay, something about the games. You know, also some games like reduction games and NIM games. I mean, the winner or the winning strategy is always taking the invariance. Sometimes say, okay, the remainder, yeah, like you draw some matches. For example, you're allowed to draw 2, 3, 4 matches each round, and then you see, okay, that's the sum of the minimum and the maximum. That's the modular. So you can always use the invariance as the strategy to win a game. Right? So in 2 moves, if you keep say, okay, no matter what your opponent take the action, you can always keep these invariants unchanged in 2 moves, and then you will have the winning strategy. Yeah. Okay. Going to show the example here. That's from the 2019 A-level. That's the Netherlands Wiskunde Olympiad final. I think this one's very interesting. Very interesting. So let's do it together. Thomas and Niels playing a game. So they have a number of cards, numbering 1, 2, 3 till a certain integer number. So start, all the numbers are lying face up. So you see already the numbers. You see all the numbers on the table. And then they play the games in alternate turns. The person who turned it choose a card and still lying. You can choose any one card on the table, and you can decide to keep this card by yourself or give this card to the other player. So that is the decision can be made. And when all the cards are gone, so each of them they just calculate the sum of the cards they have. So if the difference between these two outcomes is multiple of 3 and Thomas wins, if not, Niels wins. So meaning that Thomas needs to keep the different outcome is multiple of 3, but Niels not. So if they start with 2018 cards, okay, and Thomas plays first, Niels plays last. And we have to prove that Niels has a winning strategy. The second question is asking if they play 2 cards more, like 20 cards, and Niels start, and Thomas plays as second mover, and still, which is asking which one, but I will say Niels will win. So Niels still have the winning strategy. Okay. So there's something about, because it's the winning, I mean, the criteria of the game is dependent on the multiplication, I mean, the divisibility of 3. So then, of course, it's something to do with the remainder of the sum divided by 3, yeah? Now, the total number of cards 2018, yeah? So then every round will take 2 cards, so that's 1,009 rounds, okay? That means Thomas and Niels each take like 1,009 cards. Niels is the second player, so meaning that the last card will be taken by Niels. So he also has a chance to decide to keep this card or give this card to Thomas. But if the last card is already a multiple 3, meaning that if I give this card to Thomas or I keep this card, makes no difference, right? If the card itself, the number is multiple 3. So that's what Niels should avoid it. Otherwise, he has nothing to do at the last round because it has been determined already before. So that's why say, okay, the strategy for Niels is that try to keep the last cards is not a multiple of 3. Okay, so that's Niels can do it because Niels can select all the multiple of 3s before the last rounds because there are 18 divided by 3, those are 672 cards, which are multiple of 3. So Niels' strategy is that I always take the 3. I always take the multiple of 3s in the first round because the total number of rounds will be 1,009. So that's possible that Niels takes all the cards, all the multiple 3s before the last rounds. Okay, so that's clear. Then for the last move for Niels, thinking in this case, assume that the last number is A, which is not a multiple 3. A is not a multiple 3. And the sum of Thomas is T and Niels' sum is N. Okay, and then of also 2 possibilities because of the A is anyway the number, and Niels can keep it by itself. And then the final sum will be T and M plus A. So the difference is T minus N minus A. Of course, it can be a negative or another way around. Okay, no problem. And all give is A to Thomas. So then Thomas will give T plus A, but Niels remains unchanged. So difference is T minus N plus A. And the difference of the two difference, now that's the key to this question. Difference of two difference, 2A. And A is not a multiple of 3. 2 is not a multiple of 3, meaning that 2A is not a multiple of 3. Meaning that what? The two differences is not the same remainder, have not the same remainder divided by 3. So that must be one number which is not divisible by 3. Otherwise, if the two numbers are all multiple of 3, and then their difference should be a multiple of 3. But in the case of difference of 2A, which is not multiple of 3, meaning that at least one of these two numbers is not a multiple of 3. So that means Niels has a chance to select this case, which is favorable to him, which ensure he will win, right? So that's the one, the first question. Second question, and then Niels do the first. Niels move the first, but then we have 2020 cards. And we claim that Niels will also win, yeah? Okay, so we classified the 2020 card in two groups according to their remainder multiple of 3. So A is all the multiple of 3, B is the multiple of 3 plus 1, and C is multiple of 3 plus 2, so all the remainders. And now we calculate out of 2020, we get 673 of A cards, and 604 B cards, and 673 C cards. Oh, that's the initial stage. And what's the Niels strategy? Niels' strategy is that because he starts first, yeah, he starts first, so he can just take one A card, which is multiple 3, in his first move, and then of course after his move, the T is 0, N is Niels is 3, so both T and N are divisible by 3, yeah. And there are, because this one card is moved by Niels, so the 672 A card, 674 B card, and 673 C cards. And now it's the turn for Thomas, right? It's turn for Thomas. So Thomas, of course, they can select A or B or C cards, and then we see the Niels strategy according to what Thomas select. Okay, so if Thomas select a card from B, meaning that remainder of 1 divided by 3, and next round Niels select C, and give this to the same person that received Thomas card, meaning that the two cards, sum of the two cards is multiple 3, because this remainder is 1, this remainder of 2. So the sum of these two cards is multiple 3. So gives the same person that receives Thomas cards, meaning that the difference of T and N remains a multiple of 3. So that's the invariance. Yeah, to keep its invariance, the difference of T and N is divisible by 3. And same as Thomas selects a C card, meaning it's remainder 2, and Niels selects the B card instead. And the same reason, it gives it to the same person, and then the difference between T and N still the remainder, still the multiple of 3. And if Thomas selects the A card, of course, Niels can also select the A card. And A card, because A card is a multiple of 3, so at the end, there'll be again the difference between T and N remains the multiple of 3, because A card have 672, which is even card, is an even number, so that's feasible. Yeah, Thomas can take 1 and Niels take 1, so it's 1 plus 1 is 2. Yeah, every round you take 2 cards is possible. It's in pairs. Now looking for the case 1, case 2, because if you notice that when Thomas starts, B cards has 1 more than C cards. Yeah. So if Thomas selects C, of course, Niels is able to select B, because B card you have 1 card more. It's always possible. But in the case 1, if in some special case Thomas takes the last card of B, if Thomas takes the last card of B, and there's no C card left for Niels. Niels is not able to set C because there's one card less from C comparing to B. And what it should be done here? And let's think about it. If C means that Thomas takes B, so the T, of course, the number T is divisible by 3. No, because then you have one card more. But what about the Niels? The other card left must be an A card, because C is run out. Thomas takes the last B. So the last card for Niels must be A card, which is multiple of 3. So that means the difference between the T and the N is then not divisible by 3. Yeah, so then Niels still win, because the aim is that if the difference of the two outcomes is not divisible by 3, then Niels wins. So actually, in the second case, Niels will also win because the difference between T and N is not divisible by 3. Yeah, it's not divisible by 3. Okay, so that is the end. That is the end. Since Zhenba or Xiaomi moved to the OJ group, so in the rest 3 lectures, you are divided into 3 teams. So each team consists of 2 of you. So for this homework, Andrew and Victor will work together. Xiaoshide and Yuchen work together, and Lucy and Dingding work together. Yeah. Okay, so we have also 6 questions where you can use your knowledge learned today about invariance. Okay, I'm going to stop here.